Okay, good afternoon. Now, today we will discuss about the one of a very important subject, which is the thermal deformation. Well, composite laminate with an arbitrarily layup sequence with some plies. Then this laminate is subject to a temperature environment or boundary condition. And now we like to understand how this laminate will deform. So this is the, again, the thermal load is basically as important as the mechanical load, or sometimes even more important than mechanical load. So let me define the problem statement, what we like to solve. Let's say we have a laminate with a arbitrary layup sequence. And with some ply angles, specifications from bottom to top. And as usual, this laminate sequence is the same as the for the mechanical load. Now, instead of a mechanical load, such as the in-plane or bending moment, now we like to understand the behavior of this laminate under temperature environment, such as the, for example, top surface, for example, let's say the temperature at the top, say certain temperatures. Okay.
교수님, 죄송한데 혹시 화면 공유 주실 수 있으신가요? 예, 감사합니다.
Sorry. Right. So again, this is a laminate with a thermal loading, and at the top we have a top temperatures, and bottom we have a bottom temperature, TB. Now, when we specify the temperature boundary condition, we always need to understand the reference temperature, where our, say, reference temperatures. What does it mean by the reference temperature, which was not, the concept of reference temperature was not needed in mechanical load, because the reference load can be like the zero load. No load can be considered as a reference load, but the temperatures are different. The reason is that the strain is basically strain is a relative expansions. For example, the strain at the 0 degree, strain at the 20 degree or room temperature, the amount of deformation will be different. So let's say stress-free, and that point, the temperature, or we call reference temperature. So always what is needed is that this is the absolute temperature and the reference temperature. So this is the temperature increment at the top. And same for the bottom, we have a absolute temperature TB bottom, but how much the temperature increased from the reference. So this is the I would say temperature increment from the reference at the bottom. And now what we like to observe and we like to solve is that this laminate will deform. For example, this laminate may expand it this way. This deformation I would say the strain or shear strain, or even curvatures, all kinds of curvature, I mean 3 curvatures. So the strain epsilon 1, we simple 1, 0, 2, 0, and 6, 0. And curvature, I would say the K1, 0, well, we usually just use the K1. K1 and K2 and K6. So given temperature boundary condition at the top and bottom, what we like to know is the strain, in-plane strain, and the curvature. And also, as a result, we will have stress distributions inside the on-axis strain and stresses, and well, of course, the failure index as well. I would say the Xi-U failure index. So the this is what we like to obtain for the given thermal load. Okay, so we will drive. This is the again, we can say the problem statement. We are given this temperature, and then we like to obtain this all the strain and curvature and on-axis strain stresses of each ply, and also Xi-U failure index of each ply. Okay. Of course, all the layup sequence and material properties are given. Now, so what we like to do is that we drive how to obtain these deformations and stresses for the given stresses. Okay, so the most important point, we need to start with this stress-strain relations of each ply. Okay, the stress-strain, say this is the strain and stress. The relation is always a compliance. This is a compliance. So this is a total strain due to a mechanical stress. And now we have a strain due to a temperature increment. So this is again a total strain, and strain due to a stress and strain due to a temperature. Simply like let's consider just one simple bar. The strain will be generated due to a stress and also delta T, I mean the temperatures. So total strain will be due to a mechanical stress and then temperature. So this is the stress-strain temperature relation of the each ply. This is the most important, I mean, the starting point in these derivations. When we drive the classical laminate theory, we neglected these temperature terms, so we didn't have this term. Now, but we're gonna consider this term. Now, next step is that to get these stresses, the stresses, okay, stresses. Now, the alpha delta term will go into a left term. So alpha minus alpha delta T, alpha minus the alpha, epsilon minus alpha delta T. What does it mean? This is the strain due to a mechanical. Again, this is the total strain total strain means the strain we observe, and then this is the thermal strain due to only temperature. Now this is a stiffness, strain multiplies strain, stiffness giving us the stresses. So stress is the caused by strain caused by the temperature. We can see from this equation. Okay. Now we have a very important material property. This is the alpha. Alpha is a CTE, coefficient of thermal expansion. Coefficient of thermal expansion. In isotropic is every way the value will be the same, but in composite is anisotropic. The value is different in X direction, fiber direction, and Y direction. They are different. So this is alpha X and the alpha Y, okay? Mostly greater than 0, but sometimes they can be less than 0. And also, a very important point we need to understand in composite is that the carbon fiber is the almost a 0. So in carbon ply, we often alpha X is a very, very small value. So any structures which is made of the carbon fiber, they don't deform for different temperatures. That is very important and sometimes a very useful feature of the composites. Okay, now how about the shear thermal strain? Shear means that the shear is always the angle change. So that means if we change the temperature, the angle will change. I guess not, because this is the symmetric. So usually alpha S is a 0, no shear strain, no angle change. But if we have a certain O-axis orientation like that, then temperature increase. As you can imagine that this angle will change due to a temperature. So in this case, the alpha, I would say alpha 6 is not the 0. Okay, it's not the 0. So anyhow, so this is a starting point. And actually, this is the only difference in derivation of a classical laminate theory. Other definitions of a mechanical load and all the derivations of the strain, total strain deformation, they are all same. All same. Here, on axis, we have alpha terms. Off axis means that we have a certain angle. We have a stress in off axis, strain off axis, and the stiffness off axis. Now we have a off axis CTE as well. So again, delta T is the absolute temperature minus the reference temperatures. Now alpha bar is the off axis CTE, alpha 1 to 6. Again, alpha, this one was the alpha X, alpha Y, but the alpha S was a 0. And also carbon, this is a very small amount, very small amount. But a small amount doesn't mean it's the negligible, because the stiffness in fiber direction is also very high. So small strain may cause a lot of forces. So we cannot just neglect to 0. And sometimes this can be negative because of the carbon fiber, mechanical structures. So anyhow, this alpha 1 to 6, this is off axis, this is on axis. this is just the transformation between the on axis and off axis. We can drive very step by step, but we can simply use the tensor transformation rules, because a strain alpha is the same order as a strain, so this is the second order tensor. So simply cosine square and sine square and minus mn cosine sine, and then this. So this can be just we can use that. Okay. Again, we start with this material property and this material property. Okay, and this is the load we specify. And other material property will be obtained from these transformations. Okay, so next one is the definitions. Definitions of the in-plane load N and M, which is the same as before. I don't need to explain everything again, but I will just emphasize the key step here. Okay, off-axis stress. This is the what we just obtained from on-axis. On-axis sigma q epsilon minus alpha delta t. Now, so this is the first step, and then the second step is the, I guess, the most important point in the laminated composite, means that this total strain, okay, total strain of each ply cannot be arbitrary. Why? Because they simply bonded together, right? Bonded together. Bonded together, what does it mean? These bonded together means that they strain vary through the thickness, always a linear. Okay, so could be a uniform strain or could be a linear curvature. So as a total, we always have a linear, and this formula is from the fact that they all plies are bonded together. Okay, so this is the same as the procedure we consider in classical laminate theory. Now, definition of in-plane load and definition of a moment will be the same, right? This definition should not change. So in-plane load N should be the summation of all the off-axis stress through the thickness. And bending moment is the same thing, but here the only difference will be the Z. We need to multiply Z here to get the moment here. So note that there is a Z there. So I just want to keep emphasizing that this is the one we have to consider. This is the off-axis strain through the thickness, and this is the definitions of the load. Actually, these are all we need to consider in derivation of a classical laminate theory. And now we have a new term is due to a delta t. You can see that this is the only difference. Okay, and then we follow the same procedures, the sigma bar. Now sigma bar is this guy, so this will go in there. Now this total strain is the linear through the thickness, in-plane strain and curvature will go in there. So we substitute into this formula. So Q bar and the epsilon 0 and plus zk up to here is the same as the classical laminate theory with the mechanical load. But now we have a term due to temperatures, minus alpha bar delta t. So new term comes out here, and integration. So now let's try to integrate them. So first term, Q bar. And please pay attention to Q bar, which is the function of Z. function of z. Why function of z? Well, Q bar may vary through the thickness because each ply may have a different angle. So Q bar over axis stiffness can be different from position to position, means that it can be a function of z. So it cannot be out of integration, but epsilon 0 is the constant independent of the z thickness. So it's just the comes out of the integration. Okay, this is out of integration. Now next term is the Q bar, and then we have a z and curvature and dz. So there's a z Q bar and z, dz, and curvature. And here Q bar and z, of course, they cannot be out of integration, but k is the constant. So k can be out of integration. So this is the term, and this is the k, which came out of the these integrations. Now, this is the new term. New term is the Q bar and alpha bar and delta t. Okay, this is the Q bar, alpha bar, and delta t, and dz. So this is a new term, basically. Now, as you can see, this has to be calculated or caused by this delta t. And as you can see here, the N is just a summation of a stress. So this is the mechanical load. So N equal this Q bar integration. What does it mean? This is a A matrix, and Q bar and Z, this is a B matrix, same as before. And then we have these new terms. But new term, imagine that Q bar, alpha bar is the due to from a given material property, and delta T is the due to a mechanical, not the temperature terms. So this is the we call NT, indicating that in-plane load, but caused by the temperature distribution through the thickness. Okay, through the thickness. So this term we NT. We put into a left-hand side, and now we have a N plus NT. And then A matrix times epsilon, and B matrix times K. So A matrix times the epsilon 0, and B matrix times the K. So that is the first term. And bending moment, exactly the same as before. And then we have a new term. So here, Z term. So we have a new, the Z term here. And but here, epsilon gk, and now you have alpha bar and delta t. So this first term, Q and Z and delta dz is the one, this guy. And then epsilon 0, of course, is a constant, can be out of integration, alpha 0, alpha 0. And then here, Q, and we have a 1 Z here, and second Z here. So we have a power of the Z, Z square, dz. And then a case can be, this is the can be, sorry, this can be constant. So this is the B matrix and D matrix. Now we have a new term due to bending. I like to delete this one. Okay. So this is the new term caused by the delta T. Again, delta T cannot be out of integration because the delta T temperature can be a function of Z, which means that can be different from ply to ply. So this can be specified from temperature distributions. So this term, let's put it into left-hand side, and then we can call that moment due to temperatures. So other term will be the same. So this is a very important final equations. And this one is a newly added due to a temperature we can call thermal load. Okay, this is not the mechanical load, but the load caused by the temperature distribution, and this is the mechanical load we are applying in the laminate. Okay, so all the material property will give us this ABD matrix, and then this is the mechanical load we are applying, and now this one is the caused by the temperature and mechanical properties, and this is the newly added here. So basically, what we like to obtain is that given the mechanical load and given the temperature load, I mean, this temperature load can be calculated from this formula, and this one again. Of course, we need some steps to calculate these terms, apply to apply. But important point is the why this term. Where is this term from? And then this term will cause this epsilon zero and curvature. Very similar to a mechanical load. This thermal load will cause the epsilon and curvature. And then rest of the procedure will be the same. Once we have this, now we go to here. We get each ply we have a off-axis strain. Each ply will have this total strain, and each ply will have a on-axis, off-axis stress. In here, we need to be careful that each ply will have a delta T. Okay, we have to consider alpha bar. We should not skip this term. We have to use this one. So once we have off-axis stress here, and next one is the simply, now we go this way. We got the on-axis stress. We simply stress transformation of this, okay? And or we can just the strain transformation, epsilon, the strain transformations. Okay, so this is the all the theory we need. Rest of the procedures and pretty much same as the before. Oops. And now what we like to do is that this delta T, okay, this delta T, and at the very beginning, we specify the problem statement like the top and bottom, we have a certain temperature difference or increment. How about the inside, the temperature inside the laminate? Because as you can see here, in each ply, we need a delta T as a function of dz, a function of z. So we need to understand the temperature distribution through the thickness. Okay. Well, in general, okay, in general, the temperature may vary over the time because the temperature is the another quantity which has to meet the temperature equilibrium. Temperature equilibrium means the energy balance. You know, the temperature or heat or energy always they like to flow in a certain directions. But that temperature distribution or energy flow or heat flow is the in a way that they always the has to meet, has to follow the physical principles. So this is the temperature conduction equations. This is the del is the through the thickness, I mean, over the space. This is a T is the temperature variation over the time. And then if we consider only through the thickness, I mean, Z direction, not the x direction and x direction, y direction. The temperature variation from x and y can be neglected in a wide plate or in a general laminate. Only difference will be the variation will be through the z. So in this Laplacian, we simply change it to a kz, and then only this t second derivative with respect to a z, and this is a time. And also, if this is a fully equilibrate, then this time is also would not change. Temperature would not change over the time, just vary through the thickness. So on the left hand can be 0, and this is a term only we have. Okay, so this is a 0. What does it mean 0? This is second derivative. Means that this a first order should be always a constant. Okay, the temperature variation through the thickness z. Of course, there is a kz. Kz can be also a function of z, but let's neglect that one. Kz is always the same. If kz is the same, then this has to be a constant. What does it mean? It means that the temperature at the top and the bottom, if we have a top and bottom temperatures, then always the temperature will vary linearly like that. Okay, it's very simple but very important to understand. Top and bottom, we have a temperature specified, and through the thickness, the temperature will linearly vary. Okay, this is the very important concept. And of course, we have to understand the one assumption is that in each ply or in each layer, we have a constant kz. Well, in most cases, the kz is the constant. Why? Because we have a same ply, let's say one composite, let's say T700 everywhere. So this angle change, actually, angle change does not change the kz, because the kz is only through the thickness. This ply angle changing the xy property, so that will not change the z directional property. So as a simple case, when we have a delta t and the top temperature at the top, temperature at the bottom, we just can understand the temperature will vary linearly. Or if we know, somehow we know the temperature distribution from another analysis, like the, this way or that way, using another principle or another analysis, then just we get that temperature into our tools, and then we can obtain the deformations and all other stresses. Okay, so this is also an important point. Well, so we can consider this slide is considering all different, let's say, ply. I mean, K is the conductivity, by the way. Conductivity K. K can be a function of a K. I mean, each ply, K equal 1, 2, 3, 4, 5, and from bottom to top. And Kz is a conductivity, can vary from bottom to top plies, but you can use this derivation as a references. Okay. So if delta T can be a function of linear function of z, okay, which we just got the results because the temperature that Laplacian needs to be linear for the steady state case, and then we put this delta t into here, linear assumptions. See here, linear C and D. C and D is actually the constant we can obtain from top and bottom temperatures specifications. So I don't want to consider all the complications, but just remember that temperature can be a linear for uniform same price. Okay, that is all the equations we need to develop the Excel tools. And now Excel, we specify some, all the input is the material properties and layout sequence and temperature distributions. Now, before we try the Excel, I just want to give you on a simple just a schematic drawing why the thermal stress, thermal term can cause many different types of deformations. Okay, this is just for the purpose of understanding of the thermal deformation. Of course, we drive the older equation, but it is better to understand in a simpler way like this. So delta T, for example, we just have a 2 plies, okay? 2 ply, and each can be 2 plies or different angle, or as a simple, we can consider each ply as a say steel, or bottom is the aluminum. It doesn't need to be composite. It can be metal ply. But anyhow, when the temperature delta T, no temperature change, then they are all deformed. They are at the same length. Now we have a delta T increased the delta T. Delta T is increased. I would say the simplest case will be the uniform delta T. Top and bottom, we have a uniform delta T. Of course, delta T can vary through the thickness, but the simplistic case will be the uniform. Now, for this case, if they are not attached, if this is the case, if not glued, not glued, something is going wrong. Not glued, then each ply will have a different free expansion, right? The top one will have a expansion of alpha 1, and bottom has the alpha 2. Okay, but in reality they have to be glued together, right? Glued together. So they have to deform together. So to make this geometric constraint, we need a mechanical stress. Mechanical stress is a cause developed inside and then apply like this. This one will be in tension, and this will be in the compression. Okay, so that they can deform together. So that's why we always have a stresses inside, caused by the thermal stresses, thermal distributions. So with the understanding of this simple behavior and also all the equation we have derived, and we can now run the program. Okay, run the program. This is nothing new, and while there's not much. Okay, so the I'm sorry, I need to, okay, let's have a 10-minute break. I need to reboot. My computer is somewhat suddenly very becomes strange. So anyhow, let's have a 10-minute break. Let's start at 8:30, okay? And then we will go to, we'll run the our high CLT Excel tools for different layup sequence and different thermal temperature distribution. And let's see what kind of result we're gonna have. Okay. Okay, let's continue our class. I just opened high CLT version 313, which I distribute all to you. Now to run this case, like to remind you again, this will be just, I like to enter all the load. This is gonna be just the load case. And then the screens were shared. Share the laptop. Okay. Okay. So all you need to do is that first you choose the load option 1. 1 means simply you mean to enter the mechanical load here. So the all 0. And then as you can see, the response will be all 0 here. No strain, no curvature, obviously. So the double check the SIO index, SIO failure index, they are all 0, simply all no stresses. Now here we like to specify the temperature, and here to assign the temperature, be sure to unhide, because here we have a row 18 to 33. You need to unhide, and there is some hidden rows. And there you can specify the temperature in each ply, top and bottom, simply delta T bottom, delta T top, okay? No need to assign the reference, just the delta T top and bottom from the bottom to top all the way. So as you can see, these values are in input, and then there's another term very similar to a temperature, which we didn't cover, is the moisture specification. Due to the moisture, the strain will be generated. That procedure will be exactly same. but we will skip. Only difference will be the different material property, moisture coefficient. But anyhow, let's say we specify the temperature here, not just on the surface. This is gonna be a surface, and then a bottom surface and top surface. But in this program, we usually need to specify the temperature, not just the top and bottom, but also through the thickness that is supposed to be input. Then let's try what happens. Let's say we like to have a new window, and then to arrange all tile, and let's see the vertical. So this is the one, and then let's take a look at the output. Output, of course, all the strain and stresses will be all zero, and I'm sure the stresses and the strain will be also zero. Oops. Now, as I mentioned, we like to enter the temperatures. So temperature, this is the unit would be the degree Celsius. Let's try to consider the bottom will be the, I mean, let's say first to take a look at the layup sequence, okay? Take a look at the layup sequence. What is this? Plus minus 45, plus minus 45, and the, okay, all plus minus 45 is symmetric. This is the biaxial. Okay, this is the biaxial plus minus 45. And then let's say we apply uniform temperature all through the thickness. So let's say we increase the temperature from with respect to the reference, we increase the 100. So if we have a room temperature is stress-free, then delta T is 100, means that the absolute temperature will be 125. But you need to keep that in mind. Just this is the reference temperature. Okay, so 100, we specify the all the way from bottom to top. And then let's see what's happening in the okay, in here. See, as you can see here, I hope it's clear to you. This one is through the thickness, we have a strain of, this is an of axis, laminated strain, and 1 and 2. Actually, the green one is the strain 6. So since this is a plus minus 45, there will be no shear strain, but this is gonna extend it 1 axis and the 2 axis. Actually, this strain is the, I guess they are identical. If we delete it, you can see that. Okay, this is a 2 strain is identical. 1 direction and 2 direction is identical, simply because this is a 45, right? 45, and the strain will be the same in X direction, Y direction. Now, as you can see here, you have a stress of, and this is a plus, minus, plus, minus. So all stresses are balanced, right? All stress is balanced. What does it mean? This positive cancel out this negative. Positive, negative, positive, negative. So total stresses has to be 0. Why? Because we didn't apply any mechanical load. So this is also important point we need to observe that. And this one is a stress on, and the Psi-U, and Psi-U is the uniform, and then order of what? Order of 0.1 0.1. 0.1 actually 0.1. What does it mean? Well, if we increase the 100 degree, then the strength ratio will, SIU strength ratio will reach the 0.1. So you can see how dangerous this is. Now, let's say we have a unsymmetric layup sequence, unsymmetric, let's say very different layer. For example, 45, all 45, okay, all 45, and then but the top we have a minus 45. So the bottom we have a 45 for price, and top we have a minus 45. So this is an unsymmetric case, and then you can see what kind of a strain and the curvature you will have, and also shear strain as well. We cannot predict them physically or numerically. We only, I mean, derivation or prediction is only possible through this kind of tool. Okay. Another thing will be, let's say, minus for example, 60. Okay. Minus 60, plus 60, and minus 60, and plus 60, and then symmetric. Okay, symmetric. So 60 minus 60. Oops. Minus 60 and plus 60. Plus 60. Okay, and then minus 60. So it's all symmetric, but now is the layup is a plus minus biaxial, but biaxial 60 degree. I'd like to emphasize that the strain, okay, strain. Now in X direction and Y direction, they are different. This red and the blue and red, they are different. And of course there is no shear strain. And observe that this Y direction is a strain 2 is the negative. It's not easy to predict, but it says that X direction is extended, but the Y direction is the negative because of plus minus 60 degree. Oh, let's take a look at what kind of material property we used. Okay, we used the ply 4, and then we have to go to here, ply 4, and then material property. What kind of material property we used for the CTE? I think that okay. Yeah, I wonder there is a slightly zero. I mean the minus. That's why it's a little bit of contractions. So this is the typical value, and the 28 is also a typical value for the Y direction and the X direction. X direction sometimes is a negative like this very small amount. For example, aluminum is the order of 20 minus 6. This is the aluminum. This is the order. But here is the minus the 0.3. If this is a 0, okay, if this is a 0, then this one, I don't know how much he changed that. Let's see. So do you see the difference? Slightly difference. Huh? Okay, so this strain and the stresses, and even for the look at this Zio failure index is almost 0.3. 0.3 is the very high, right? 0.3. So if we have a biaxial 60 plus minus 60 and temperature increased to 100, then the stress will be caused inside a lot. Okay, that's the one feature we can. This is one case we can try. And again, for uniform temperature, you can even try the temperature decrease or contraction. And then we can try many different layup sequence. Okay. Now, with this layup sequence, of course, we can consider temperature distributions of through the thickness. Okay, through the thickness. See, as we observe in here, okay, in here, temperature is the temperature can be specified. Actually any temperature we can specify through the thickness. So if this is a bottom top, okay, first ply is the bottom, right? So this is the bottom of the bottom ply, and then increase, and then so expand, and let's say the top and the bottom. Now bottom will be simply, okay. This one, top, you can say this is the same as that one. So we can say this because they are contact. Okay. Let me just arbitrarily assign the temperatures. We have a 24 plies, and then let's say we just okay, this is just an arbitrary number. Okay, just the decrease the 2 degrees from each ply. So as you can see, 198 and etc. and decrease, and then well, you can say it's gonna be a 52. So temperature simply vary through the thickness. Something like that. Okay, temperature at the bottom is the hot, and the top is also hot, but okay, let's try to. Okay, for this specification, let's take a look at the temperature distribution, the strain distribution and curvature distribution, and etc. You can see that it's very difficult to say why this is this much slope, why this is the zigzag, and etc. It's kind of difficult. We could, but it takes a lot of effort to quantify or qualify the behavior. But as you can see, how important these tools and theory. Okay, so you can imagine that what kind of thermal behavior, you can calculate all kinds of deformation, analyze the thermal behavior due to a temperature distribution through the thickness. Okay. Now, let's say since we went through all the equations, I just want to make sure that the theory we used is the same as the what we have. Okay. So this temperature distribution. In the next step, we go to TK. TK is the K and top and bottom temperatures. And then next step will be slope and constant. Okay, this is slope and constant. Well, if we click this one, is a slope and constant. What does it mean, slope and constant? This is nothing but the temperature distribution through the thickness. So slope and constant. And as you can see, this is the formula, and this is the formula. Oh no, this is the formula, and this is the formula. Okay, actually, this is the equation we derived from here. So that is the from this each ply we have okay, this formula, and the next formula we will is the that one. The more important point is the NT. NT is the what? NT is the thermal temperature, thermal terms due to temperature, and as you can see here, Q11 times the alpha 1, Q12 times the alpha 2, and Q16 times alpha 6, and the Q and so on. Where it come from? This is the that is from here. Here. Okay, let's see. Let's see, we have any simpler form. Okay, well, important point is the this term. Okay, this term. Delta T is the a slope and constant through the thickness. Actually, the I would say slope times z plus a constant. That is the delta T. Okay, and then remember alpha times Q bar times alpha. This is the 3 by 3 and matrix multiplications. That's why, as you can see here, we have a see here slope and Q alpha 1, Q12 alpha 2. And so this is the expansion of the matrix multiplications, matrix and vector, right? And same for the N2. N2 now, instead of a Q11, you have a Q12 and the alpha 1. And you can see that you can now is alpha 16. And moment, now you have a Q11 and Q12 slope is over the divide by 3, because the we assume the temperature vary through the thickness. Okay, so this is the thermal load we as we derived from theory. And then this is the moisture, which we didn't consider, but this will be the same as the one. So thermal for each ply, okay, each ply thermal load, and then on the right-hand side, we just add them here. As you can see, this is all summation of one row. Then this guy will, where will this term go? This term will go to now ABD matrix multiplications. As you can see here, the if we click here, we have a thermal load and mechanical load. So we add them here, and then multiply the ABD matrix, and then we inverse the ABD, and then thermal and mechanical load will give us the this strain. Okay, this is strain. Once we have a strain and curvature, what will be the next? Obviously, the next step will be go to every ply we get the strain. Okay, every ply we get the strain. Why? Because the strain is given as a epsilon 1 in-plane strain, and curvature which we obtain, and then is z coordinate and every ply. Okay, so ABD matrix, we got the in-plane strain curvature. Once we have an in-plane strain curvature, now we can get all the strain in every ply. And then what will be the next step? Next step will be stress strain curve, of course, and stress strain curve here. As I well, this is just the you can transform stress strain transformation. Okay, stress transformation. And then stress, when you get the stress, as I said, is very important. Easy to make a mistake is that Q times strain. Okay, now don't forget we have a alpha delta T. Okay, we have a Q times strain minus alpha delta T. And of course, there is a moisture beta term, but point is that Q strain minus alpha delta T, okay, Q minus strain minus alpha delta T, that is the what? That is the this term, okay, Q strain minus alpha delta T. So what we just observe is the looks complicated, but every theory is in this one page. Again, temperature distribution, which is a model as the slope and constant. And here, this term is considered as the thermal load. And then we get the ABD matrix, we get the strain and curvature. And strain curvature, we get all the prime strain, this one. And then this got, once we got this total strain, each ply will have a stress, OB-axis. And then on-axis stress. And then what will be the final step? Of course, the failure index to calculate Xi-O failure index. Okay, so this is the one of the very important feature of the classical laminar theory. Again, not just the by the mechanical load, but the thermal load. Thermal load can cause deformation and cause the stresses, and sometimes as high as the material failure. Okay, the material may fail. Oops. Oops. Okay, while you of course, since you already have all the tools, you should be able to run all the tools. Of course, with understanding with all the theory, you don't have to develop a very complicated tools. Actually, you can do it yourself, but just save your time and effort. I share with you all the tools and theory, but be sure to how to use it. Be sure to understand all the theory. Okay. And then our next week, or this Friday, we will have another class, very important class. We have a Saturday, we have a class. In that class, we have two classes. One first is the 2 hours, and the another after 1 hour, we have a second part. That is the we're gonna have a TOM project. TOM project means that we're gonna not the TOM project. I don't want to call it TOM project. We're gonna have a kind of a mixture of the exam and then TOM project. Means that in 2 hours you come with all the tools ready in your computer. And then whenever I specify, you quickly run the case and they get the result and the report. Okay, so that will be the format of the final exam this Saturday. Okay, basically we went through most of the theory. We like to cover this semester, but again, since we have to do a more class, I'm gonna do a more class on this Saturday. Okay, okay, let me. Okay, I will just use the top. Okay, I'm gonna.
Professor, can I ask a question?
Sure.
The thermal load, if I want to design a composite laminate, but I don't know the thermal slope inside. I only know outside at the top and the bottom, but I don't know the thermal load, the slope. How can I design it? I
Yes.
don't know the temperature
Yes.
inside, how it the
Sure.
flow inside.
Yes, as I mentioned, the temperature
Yeah.
distribution through the
Yeah.
laminate, okay,
Yeah.
has
Yes.
to be obtained by solving temperature equilibrium. For example, temperature equilibrium is a different physics.
Yes.
Our temperature equilibrium. Laminate through the thickness, for example. Okay. Sometime this is not the temperature equilibrium in a laminate. Okay. For example, as you can see here, this is a temperature vertical. This is through the thickness. We have a different coordinate, but you understand that different through the thickness, we have a one layer, and the second layer is happen to be very thick, and third layer. And the first one is a stainless steel and carbon
Okay.
steel and stainless steel. Doesn't need to be composite, okay?
Yes.
Now we because of some boundary condition or some condition, the temperature distribution along with the time. This is I guess not the temperature. This is a time.
Yes.
Time goes by, the temperature distribution will change like that.
Yes.
Because this is a heat transfer. Heat transfer is, as I mentioned, you need to solve the temperature equilibrium. Equilibrium in conduction, usually in conduction is a simple. There's a temperature gradient over the time, and
Yes.
also temperature gradient in the through the thickness, temperature distribution. This
Yes.
is the conduction,
Yes.
but the transient. So, but this surface may subject to a convection condition,
Yes.
or a very different boundary condition, which is not gonna cover in our class. So
Okay.
any the temperature distribution you get, and then you enter and you get the stresses. The simplest case will be no transient,
Yes.
steady, and this is the constant Kz. Then this will be a constant. So constant means that you need to enter sort of as I mentioned,
Yes.
this one. So this is the constant. So at the bottom you specify 100. At the top you specify the 50 degree. Okay, 55. Yes. Then middle side is automatically constant. Why? Because this way is it satisfy the temperature equilibrium. So in this case, you don't need to calculate temperature equilibrium. You only need a top and bottom, and through the thickness is a linear. But in general, you have to solve the temperature equilibrium. Okay?
Okay, thank you.
So December 16, and the first we have a class from 12:30 to 14:30, right? 2 hours. We will have a Q&A. You can have questions, and I will answer, or I will just check some issues, some design, and some important. This is just gonna be a kind of a review. But very important is the for your Q&A. Okay, anything will be okay. We don't have any homework today, but you better practice the thermal term for sure. Okay, you have to do it. Now, the second, the time after 1 hour, we have a 15 and 30 to 17:30. This is also 2 hours. We will have a exam. Exam, I would say we're gonna have 1, 2, 3 questions. I will get ready this tool, okay? High CLT, your own high CLT. You have to have them ready in your computer. So when you come to a Zoom, you have to have your own CLT ready to run that. Make sure your high CLT runs well in your computer with a Zoom, okay? So you have a Zoom ready, I mean the class and CLT. Make sure this is the runs well, okay? So we're gonna have an exam, the question 1 and question 2 and question 3, okay? So question 1, for example, I'm gonna explain, okay? I'm gonna just explain, say 10 minutes, and then I will give you 30 minutes for solution, and another 10 minutes. Okay, 10-minute Q and 30-minute answer, and 10-minute Q and 30-minute answer, and 10 minutes Q&A, Q, and then question, 30-minute answer. Okay, so when you have a answer, you need to get the results. Okay, result, and put it into a PowerPoint PPT file. Same thing. Well, you can call it exam, but not just the just question. I'm gonna give 10 minutes. I'm gonna explain situation and question, and give you a 30 minutes. You get the result using the high CLT, and then get the result and put it into a PowerPoint very quickly, and then same thing. Okay, so after 2 hours, you submit this PowerPoint. Any question about that one? Now here, very important point is that you know, the your homework so far. Well, some submit regularly and on time, but some didn't. Now you have to this Q&A, this answer, this one has to be and the last section of your PPT. So for example, homework 1, you got the submission, right? This has to be a one file, by the way. So homework 2, you have a one answers. Homework 3 and 4 and 5 and 6 and 7 and the 8 and 9. And now next one will be you say add a section, and you're gonna say the final. And then you can have you're gonna have a question 1 and question 2 and question 3. Of course, you can have several slides for each questions. but this is the format we're gonna go through. Okay. Any questions? Yeah, there are some lecture notes missing. I didn't upload that. I will try to upload tomorrow, but today is a Wednesday and Thursday and Friday and Saturday. We don't have much time. To upload the YouTube, I need to edit. That's why it takes some time. But I will try. I will upload the last missing. I guess we missed 2 classes. Well, 1 classes. Okay. Of course, I will upload this today's class as well. YouTube. To YouTube. Any question about the format of the this Friday's test? Because we need to have a class first 2 hours, and then we'll followed by the final exam 2 hours. So I highly recommend you to get ready, practice, run the CLT. What will be the input? What will be the output? And then mechanical load and the thermal load, and also you know, the quick chart. You have to run the quick chart. Well, not that difficult, but as you can see, the high CLTs are so powerful tools, and it contains all the theory we covered in this class. Any questions? If not, okay, this is the end of today's class. Okay, see you this Saturday at 12:30. Sorry, it is lunchtime, but please have a early lunch or a late breakfast, and then I'll get come to class. Okay, if you have any further questions, and please share through our cutoff. Okay, thank you.